can affect, let's say, the transformation of the smart cities. So basically, what I'm going to discuss today is about the smart city innovation and what is expected on the 5G. 5G is not only about new capacity and capability, but it's a new way of redesigning the network. One aspect that will affect in this transformation is what is called edge and fog computing, is the area when a lot of data needs to be processed, something which is important for a smart city use case scenario. And I will present finally some use case scenarios and some potential analytics that can be applied in smart cities. So when we discuss about smart city innovation, we can see and think of two different types of innovations from the application point of view. One is the smart management of the infrastructure. We have use case scenarios related to smart metering, to smart governance, to how to be able, let's say, to protect the environment and to create a sustainable environment. And of course, safety, security is an important aspect. And of course, apart from the let's say applications related to the management of the infrastructure, we have also applications and benefits for the people, starting from smart health care to smart mobility and transportation, to smart campus, and of course, smart surveillance. In order to facilitate all these applications, we need to think about technologies that are important, all right, to be deployed in a smart city environment. Starting, let's say, from the bottom, we need different IoT devices that needs to collect different types of data. Then a network that we need is a kind of 5G type of network that has the capability to scale up in an efficient manner. So we have something which is called network softwareization. I'll discuss later on this concept. The cloud, you may have different types of cloud. Besides the central model that we use today, we have also different types of edge infrastructure that can be deployed on the edge. And then it's about managing all this data and using AI models, how to generate smart analytics. And of course, all this information has to be linked with some geographical information. So what we expect from 5G? First of all, besides, let's say, the new capability that it's going to be dozens of times faster than the existing 4G systems, and besides the connectivity of everyone, we are here in 5G, we are discussing about connecting of objects. So we can facilitate machine-to-machine communication, allowing objects that can be deployed in a city to be communicated in automatic fashions. It has to be environmental friendly. The previous speaker discussed about the energy footprint. So energy consumption and energy efficient is a critical factor. And it has to be reactive, which is especially important for real-time services. For example, when we discuss about connectivity of cars, or if we have an incident, how to be able to handle that in a relatively short time. In order to meet these expectations, 5G has to be flexible. That means it has to use open standards. We discuss about the introduction of softwareization. So the network infrastructure has to be programmable, and this programmability has to follow the agile principles. Apart from that, the network has to be robustness. That means it has to scale up in an efficient manner based on demand. It has to be secure and reliable, and then it has to follow certain standards. So if we want to discuss about the network evolution and what the 5G brings, according to ITU, 5G and the use cases are under three pillars. One is the enhanced mobile broadband. So we are discussing about capacity in the order of 10 gigabits, even and higher bit rates are expected to come in the future. So for this kind of capacity may be required for applications like video augmented reality or virtual reality. We have the ultra low latency, which is important for applications related even to self-driving cars or for industrial automation. And finally, the connectivity among objects, the machine type of communication, and this has an application to a use case scenario related to smart buildings, energy and utilities, logistics, etc. A key element, as I mentioned, is the softwareization. So an important technology for that is the virtualization technology and the evolutions. So we started with the virtual machine, which is, let's say, the possibility to host different operating systems in let's say, in a server. This kind of approach follows the waterfall model regarding application deployment. And the evolution of that is the containers and unikernels. And the reason for this evolution is to reduce the overhead and the computing footprint for the application provisioning. And by doing that, we can follow the agile model in terms of application development and deployment. And then using that, we can, let's say, develop the applications, what is called cloud native approach. That means instead of following the old monolithic approach for application development, you can decompose, let's say, each application to different services, and based on demand, you can scale the services. All these technologies regarding softwareization plays an important role to the evolution of the network. So a key, let's say, evolution is the introduction and being able to, let's say, deploy network functions as network entities. So the technologies in this category are called cloud native network functions. Network functions are based on microservices, as I described before. Network function virtualization, so basically separating the network service from the hardware infrastructure. So in a nutshell, a network entity like a router can be a software entity. And in order to do that, we need software which is called orchestration, and its role for that is to be able to deploy such software elements based on the demand. An evolution also of the network introduces also some other, let's say, functionality. One of them is software-defined one that facilitates the virtualized network overlays in order to be able to provide the end-to-end WAN connectivity. Network slicing that can create different virtual networks over the physical network based on the demands and the requirements. And finally, the Open RAN, Open Radio Access Network. So it's about the disaggregation of the hardware and software solutions on the radio access using open hardware and open interfaces. All these are technologies that are related to softwareization. On the other hand, we have evolutions how to improve the capacity on the wireless. That is massive MIMO that we can have multiple ultra narrow beams for coverage and improve throughput, and the use of millimeter wave, so the spectrum above 6 gigahertz to improve the throughput, especially in the context of smart cities. All of these, let's say, technologies can be captured in this figure. So this figure illustrates on the bottom the 5G different radio technologies and how these technologies can receive information not only from devices, but also from other types of infrastructure that can be drones, that can be cars, even IoT objects. At the layer above, you have the softwareization layer in order to be able to facilitate all the functionalities. And finally, at the top, the business application layer. Another important element in 5G is how to automate, let's say, the functionalities. And these functionalities related to the planning and design, how to meet the user and service requirement, how the deployment of the network can be done on these software entities that are described, and how the service deployment, the service chain also is facilitated in order to meet the user of experience requirements. Another important element is the operation and maintenance of the infrastructure. That means if there is a stress in a particular entity, how to do the resource adjustment through the auto scaling, and whether there is a need for policy adaptation and also to support mobility. In order to do that, you need also specific tools in order to detect potential anomalies in the traffic and in the workload, to identify potential faults and to do the recovery. And finally, security by design is a must on 5G, how to do a deep packet inspection to cope with the security vulnerabilities and threats, and to isolate potential infected components. This automation is also bound with the self-organization. In our days, the networks are managed and maintained by network engineers. So we are expect in 5G and beyond, things will become in automatic fashion. So we won't need in the future, hopefully, network engineers. And when we're discussing about self-organization, we have four pillars. One is the self-configuration, how to do the configuration of each network device automatically, like a plug and play. Another important aspect of the network is the self-optimization, how to be able to meet the user expectations and to be able to deal with the bandwidth, the interference and mobility. We need to self-learn from different elements of the network. That includes different network elements, the subscribers, and what is happening in a particular location. And finally, self-healing. Self-healing means that if there is a problem in the network, either a fault or let's say, a congestion on the network, how to be able to mitigate these problems in an automatic fashion. An important element of the network, especially on 5G, is the concept of edge and fog computing. The fog and edge computing is the concept of shifting the computing data center that we use centrally nowadays close to the end user. The end user in 5G can be either Internet of Things, it can be a mobile station, or it can be a gateway that has been installed, let's say, in our premises. The fact is that in our day, over 90% of the enterprise data are sent to the cloud, but we expect by 2025 this number will drop to just 25% because everything will be done on the edge. And then we have different standards to handle the edge. We have the ETSI multi-X cloud computing, which is basically a working group within ETSI dealing with the extension of the mobile network, basically the mobile base stations to have computing capabilities. And we have also the Open Edge Computing and Cloud Native Computing Foundation dealing with APIs to deploy applications on the edge. And at the same time, we have also consortia that are, let's say, coming from the IoT world, that is the Open Fog and the Industrial Internet Consortia, looking how edge are linked with the IoT. The difference between the edge and the fog is mainly the fog is referred to a more lightweight device, which is more appropriate for IoT type of applications, where the MEC nodes is linked mainly with a mobile network. So the owner of the MEC node can be a mobile operator, where the owner of the fog node can be any third party that has an interest to deploy an IoT type of application. So if we look at the edge cloud value chain, at the bottom you have the edge location owner that can be either a mobile let's say, provider. It can be the enterprise, it can be a smart car, it can be a stadium, or it can be a smart factory. On top of that, we need the edge connectivity layer that also deals with the orchestration, how to be able to deploy different functions on these edge devices. And finally, we have the APIs and the application enablers, which are important in order to host different types of applications. The edge requirement has to do with the scalability, how to be able to deal with the distribution and the optimal points of deployment. We need, of course, security by design, as I mentioned, since we deal with analytics and information that may be collected by end users. We need to make sure that there is no violation on GDPR. In some cases, there is a requirement for a very low latency in order to optimize performance. One of the things in nowadays is what is called zero-touch provisioning, how to initiate the deployment, the management in a relative short time. And for TESAL applications, it can be providing of contextual information, how to do traffic redirections, or how to do smart analytics, as we will see on the use case scenario on the final part of my presentation. One aspect of the edge is the FPGA acceleration. At the moment, the easiest way to achieve performance is to use CPUs. For CPUs, there is a bottleneck regarding the latency, which is in the order of 50 to 100 milliseconds. If we want, if we need basically networking and security functionality with a much better latency response in the order of few microseconds, we can use specialized hardware that can manage and optimize in a parallel way the data processing, and that is the FPGA. Another area that is important is how to be able to do and run AI machine acceleration models in the hardware. There are already available solutions from the market, from Intel, from Google, from NVIDIA, even from Apple. And this kind of hardware, it can be considered as appropriate for high-intensity computing applications. Now, another motivation for the edge is basically instead of following the conventional AI processing, is to be able to run part of the machine learning model on the edge. Then more complex deep learning models can run on a central system, and I have a figure for that. So here the idea is to use what is called federated learning. So the idea is we can run in a distributed fashion a small machine learning model that can run local on the edge. All these local models are aggregated centrally on the central cloud that has the resources to run such complex deep learning model, and this complex model is sent back to the edge. And this is something which is called federated learning. So how to be able, let's say, to bind federated learning and edge is shown in this figure. I'll skip some of the slides because of I can see that we're running out of time. There are a lot of and there's a lot of interesting by the research community regarding edge cloud projects. Just to refer some of them, Acreno, X Foundry project, Eve, Fledge, Home Edge, State of the Edge, Open Horizon, Battle and Secure Device on board. And all these are, let's say, open source project related to the edge cloud. So edge cloud is an important element for smart cities. Finally, I would like to see to show some of the scenarios and some of the data that can be processed in a smart city. Typical application scenarios range to face recognition, object recognition, activity, augmented reality, caching for CDN, and V2X communication. Now, as we understand, we need to have and process data. We can have three types of categories. In the first category, we can have low requirements from the AI perspective. That means data that can be captured, let's say, from a person. So can have analysis related to activity or to sensor analysis. Medium analysis when we can need to analyze audio and signal. And finally, the high requirements, it has to do with analysis of the video and what is called video analytics. So as we understand, the video is something that is the more challenging because of the data and the overhead that is introduced. In the context of smart video analytics, we can consider applications, how to be able to estimate the number of people in a smart city, how to do also face detection and face recognition, how to do behavior analytics, and how to do gender identification. All right, that's the end of my presentation. What I present today is basically the innovation, the transformation that is needed in a smart city, how the 5G and the different technologies can lead to these transformations, and I presented some typical use cases related to AI and analytics in a smart city.